Okay, in the ALEKS section 3.4 handout, the first item we have to be the difference between base 7 logarithmic terms. Here we had the base 7 logarithm of 8 minus the base 7 logarithm of 9. And once we consolidate and write as a single base 7 logarithmic term, okay, anything that stems from positive terms, the attachment is going to be in the numerator. Anything that stems from negative terms, we're going to have in the denominator. So we have, in the end result, we had the base 7 logarithm of 8/9. Now, for what we have in the case of the second part, so we have a base 3 logarithm of 8. And we have plus base 3 logarithm of a missing term. And we'll say we just have of x is equal to the base 3 logarithm of 40. And once we look at determining what is to be put in the blank, all right, again, we have addition of base 3 logarithmic terms, and addition is going to imply multiplication. So we will have a base 3 logarithm of 8 times x is equal to the base 3 logarithm of 40. And since we have single base 3 logarithmic terms, I can set the attachments equal to each other. So we have with 8x equal to 40, we have x is going to be 40 divided by 8. So we have, in this case, we have that to fill in the blank, okay, that is going to be the value 5. And now for what we have for the third part, we have a base 8 logarithm of 32. And we have is equal to 5 times the base 8 logarithm of a missing value, and I'll just say I have x. Now, going back to what we have in expanding and contracting operations between logarithmic terms, we have situations where you can write exponents as coefficients and vice versa. Now, if I'm looking at solving for x, what I can do over to the right is to convert that 5 into an exponential power to which x is going to be raised. Okay, so we have going from 5 the coefficient to an exponent, we have the base 8 logarithm of x to the 5th, and with the attachments set equal to each other. So we have 32 is equal to x to the 5th. And in solving for x, I can just take the 5th root of both sides. And 32 is going to be, in this case, right, you have 32 is 2 to the 5th. 5th root of x to the 5th goes to x. And think of it like 2 to the 5th. 5th root of that is going to cancel out what we have between the index number of the radical and the power to which 2 is raised. And so we have for the missing value x, that is going to be at 2. Now, for what we have in the case of item number 2, it says to use the properties of logarithms to expand the logarithm in base 10 of y to the 8th over z. So we have for base 10 logarithm of y to the 8th over z. Again, we have division, and division is going to imply subtraction. So we have base 10 logarithm of y to the 8th minus the base 10 logarithm of z, and converting any exponents into coefficients, we have for the end result, we have 8 times the base 10 logarithm of y minus the base 10 logarithm of z. Now, for what we have in the case of item number 3, we're looking at expanding once again, and we have base 10 logarithm, so we have the cubic root of x to the fifth divided by the product of y squared and z. And where I have radicals, I'm just going to go ahead and convert these, or in this case, this item, as x expressed as a power that is a non-integer value. Okay, so in this case, we have x to the 5/3, and we have all over y squared times z. And we have three factors, one in the numerator, two in the denominator. And looking at expanding, anything that is at the top is going to be a positive logarithmic term. Anything that is at the bottom will be negative. So here we're going to have negative base 10 logarithm of y squared, followed by a negative base 10 logarithm of z. And writing exponents as coefficients, we have for the final form, we have 5/3 the base 10 logarithm of x minus 2 times the base 10 logarithm of y, and we have minus the base 10 logarithm of z. Now, for what we have in the case of item number 4, okay, we have yet another expansion. And for what we have in this case, right, we have base 10 logarithm. We have of 6 times the quantity of x plus 5 raised to the second. And we have all over the cubic root of x to the 4th. And if I rewrite the radical as an exponent, so just modifying the ratio. Okay, so we still have 6 times the square of x plus 5. And this is going to be all over x raised to the 4/3. And looking at what we have and expanding. Okay, so you have two factors at the top. So we're going to have positive base 10 logarithmic terms. So the base 10 logarithm of 6, followed by the base 10 logarithm of the square of x plus 5. And we have minus the base 10 logarithm of x to the 4/3. And converting the powers as coefficients. Okay, so we have between base 10 logarithm and 6. Okay, 6 is not an integer power or a factor of 10. So base 10 logarithm of 6 remains fixed. And we have for the next terms, okay, we have 2 times, okay, the base 10 logarithm of the quantity of x plus 5. And we have for the last term, we have minus 4/3 of the base 10 logarithm of x. Now, for what we have in the case of number 5, as well as number 6, okay, we have number 5, we were looking at condensing as a single logarithmic term. So we have 1/2 times the base 6 logarithm of w, and we have plus 2 times the base 6 logarithm of x, and we have minus the base 6 logarithm of z. And in terms of condensing as a single base 6 logarithmic term, okay, wherever we have coefficients other than 1 out the front, we're going to adjust, changing and modifying from what we have originally to exponents. So you had the base 6 logarithm of w to the 1/2 plus the base 6 logarithm of x squared. And again, we have minus the base 6 logarithm of z. And as we combine as a single base 6 logarithmic term, first two terms are positive, so we have w to the 1/2 and x squared at the top. And in the denominator, okay, we have z. And where we have fractional exponents, you can also write the result as the base 6 logarithm of, and just we can switch the order. Say we have x squared, w to the 1/2 will be the same as the square root of w, and we have all over z. For what we have in the case of number 6, we have 4 times the base c logarithm of y minus 1/2 the base c logarithm of w, and we have plus 6 times the base c logarithm of z. And adjusting the leading coefficients, changing them over to exponents. So you have the base c logarithm of y to the 4th minus the base c logarithm of w to the 1/2. And we have plus the base c logarithm of z to the 6th. And putting together what we have here, we had the base c logarithm. Okay, first term is positive, so the attachment is going to go to the top. Next item is negative, so w to the 1/2 goes on the bottom. Last term is positive, so we have z to the 6th at the top. And we have, once again, with w to the 1/2, you can also express the result as the base c logarithm of y to the 4th, z to the 6th, all over the square root of w.